Let us look at the first lemma. Let A be a matrix with entries aij, be written as A1, A2 up to An, with size n by n, and B be a matrix written as B1, B2 up to Bk, be an n by k matrix, where Ai and Bj are the columns of A and B respectively. We also let X equals the column vector x1, x2 up to xn. Then A times X equals x1 times A1 plus x2 times A2 up to xn times An. Also, A times B, which is equal to A times the matrix B1, B2 up to Bk, equals the matrix with columns A times B1, A times B2 up to A times Bk. For the first point, A times X is equal to the matrix A11, A12 up to A1n, A21, A22 up to A2n, and so on, until AM1, AM2 up to AMn, times the vector x1, x2 up to xn. This matrix vector product is a column vector with entries A11 times x1 plus A12 times x2 plus all the way to A1n times xn. A21 times x1 plus A22 times x2 plus all the way to A2n times xn. This carries on until we have AM1 times x1 plus AM2 times x2 plus all the way to AMn times xn. We observe that each entry is a sum of n terms, so we can break this off into the sum of n columns. The first one is A11 times x1, A21 times x1, up to AM1 times x1. The second column is A12 times x2, A22 times x2, up to AM2 times x2. The last column is A1n times xn, A2n times xn, up to AMn times xn. We observe that in the first vector, we have a common scalar multiple x1, so we can take it out. Similarly, we can take out x2 in the second vector, and so on. So we have x1 times the vector A11, A21 up to AM1, plus x2 times the vector A12, A22 up to AM2, plus all the way to xn times the vector A1n, A2n up to AMn. Since each vector is a column of A, this is equal to x1 times A1 plus x2 times A2 plus all the way to xn times An. For the second point, let C be the matrix with columns AB1, AB2 up to ABn. The ij entry of C is equal to the ith entry of the jth column, so it is equal to the ith entry of ABJ, which is equal to the ith row of A dot Bj, which is equal to AI dot Bj, so it is equal to the ij entry of A times B. In other words, the ij entries of C and A times B are all the same, so C equals A times B. Let's look at the second lemma. Let A and B be n by n matrices, and let x and y be n by 1 column vectors. The first point is that A times bracket x plus y equals A times x plus A times y. The second point is that A times bracket k times x equals k times bracket A times x, which also equals bracket k times A times x, where k is any real number. For the third point, bracket A plus B times x equals A times x plus B times x. To prove them, let A be A1, A2 up to An, and B equals B1, B2 up to Bn, be expressed in terms of their columns. We also write x equals x1, x2 up to xn, and y equals y1, y2 up to yn. For the first point, A times bracket x plus y equals A times the column vector x1 plus y1, x2 plus y2, up to xn plus yn. Using the first point of the first lemma, this equals bracket x1 plus y1 times A1, plus bracket x2 plus y2 times A2, plus all the way to bracket xn plus yn times an. We can expand the brackets to get x1 times A1 plus y1 times A1 plus x2 times A2 plus y2 times a2 plus all the way to xn times an plus yn times an. We can group the terms with x and group the terms with y to get bracket x1 times a1 plus x2 times a2 plus all the way to xn times an plus bracket y1 times a1 plus y2 times a2 plus all the way to yn times an. Using the first point of the first lemma again, this equals a times x plus a times y. For the second point, a times bracket k times x equals a times the column vector k times x1, k times x2 up to k times xn. Using the first point of the first lemma, this equals bracket k times x1 times a1 plus bracket k times x2 times a2 plus all the way to bracket k times xn times an. Using properties of scalar multiplication, we can change the positions of the brackets to get k times bracket x1 times a1 plus k times bracket x2 times a2 plus all the way to k times bracket xn times an. By taking out the common factor k, we get k times bracket x1 times a1 plus x2 times a2 plus all the way to xn times an. Using the first point of the first lemma, this equals k times bracket a times x. We also have the third expression, which is bracket k times a times x. Using the first point of the first lemma, this equals x1 times bracket k times a1 plus x2 times bracket k times a2 plus all the way to xn times bracket k times an. Using properties of scalar multiplication, this equals bracket x1 times k times a1 plus bracket x2 times k times a2 plus all the way to bracket xn times k times an. Since the set of real numbers is commutative, we can swap the positions of the xi's and the k's to get bracket k times x1 times a1 plus bracket k times x2 times a2 plus all the way to bracket k times xn times an. Using properties of scalar multiplication again, this equals k times bracket x1 times a1 plus k times bracket x2 times a2 plus all the way to k times bracket xn times an. We can take out the common factor k to get k times bracket x1 times a1 plus x2 times a2 plus all the way to xn times an. Using the first point of the first lemma, this equals k times bracket a times x. For the third point, bracket a plus b times x equals the matrix with columns a1 plus b1, a2 plus b2, up to an plus bn, times x. Using the first point of the first lemma, this equals x1 times bracket a1 plus b1 plus x2 times bracket a2 plus b2 plus all the way to xn times bracket an plus bn. We can expand the brackets to get x1 times a1 plus x1 times b1 plus x2 times a2 plus x2 times b2 plus all the way to xn times an plus xn times bn. We can group the terms with a's and group the terms with b's separately to get bracket x1 times a1 plus x2 times a2 plus all the way to xn times an plus bracket x1 times b1 plus x2 times b2 plus all the way to xn times bn. Using the first point of the first lemma again, this equals a times x plus b times x, and the proof is complete. For the third lemma, which is also the last one, let A be an n by n matrix and B be an n by k matrix. Then A times bracket b times x equals bracket A times b times x, where x is any k by 1 column vector. For the proof, we let B be b1, b2 up to bk be expressed in terms of its columns, and write x equals x1, x2 up to xk. Then A times bracket b times x equals A times bracket x1 times b1 plus x2 times b2 plus all the way to xk times bk, using the first point of the first lemma. Now, using the first point of the second lemma, we can multiply A inside the bracket to get A times bracket x1 times b1 plus a times bracket x2 times b2 plus all the way to a times bracket xk times bk. Using the second point of the second lemma, we can take out the scalars xi to get x1 times bracket a times b1 plus x2 times bracket a times b2 plus all the way to xk times bracket a times bk. By the first point of the first lemma, this equals the matrix with columns a times b1, a times b2, up to a times bk, times x. From the second point of the first lemma, this equals bracket a times b times x, which completes the proof.